The race for dominance in generative artificial intelligence has just stepped up a gear. One of the leading companies in the field has unveiled its latest chatbot. It has advanced capabilities including seeing, hearing, and talking in similar ways to a person.
Similar ways to a person.
AI is the new reality in classrooms across the country.
What people don't seem to understand is that these language models are designed to produce language, not make claims to the truth.
AI by itself is like raw brain power. It's got all this potential, but it's not really useful until you give it a job. Enter the AI agent.
So I think we're going to live in a world where there are going to be billions of different AI agents, eventually probably more AI agents than there are people in the world.
AI. It's here, it's now, but did anyone actually ask for it? And how will it affect how we teach and how we learn? Hello and welcome back to The Secret Life of Language, a podcast from the School of Languages and Linguistics at the University of Melbourne. I'm Professor John Hajek.
And I'm Dr. Yu Hao. Thanks for joining us for this second of a series of episodes in which we look at how generative AI is impacting teaching and research activities in university settings, and with a special focus on the areas of languages and linguistics.
Now, in our first episode, we talked about ethics and policy challenges around using generative AI in universities. We deliberately shied away from the more technical explanations and jargon to do with the technology, I suppose because we didn't want to scare off listeners.
Yeah, for those of us who aren't software engineers, data scientists, or deep learning specialists, getting to even a basic understanding of how generative AI does its magic can seem rather daunting.
But just treating products like Google Gemini or ChatGPT purely as black boxes is probably also not very wise, as it can lead one to get the wrong idea about what users can expect from them, both in terms of their jaw-dropping features and their considerable limitations.
So in this episode, we'll be taking a glimpse under the bonnet of generative AI, and because we are language people, spent some time demystifying some of the generative AI jargon that even casual users are coming across. One of the people we spoke to shed some light for us was NLP expert Dr. Frermann.
My name is Frermann. I'm a senior lecturer in the School of Computing and Information Systems at the University of Melbourne. And my specialty is natural language processing, where we try to teach machines to understand and produce human language. And I'm also very interested to use these methods that enable automatic natural language generation and production to better understand how humans learn language, use language, represent common sense knowledge, and so forth. So I'm at the intersection of natural language processing and computational cognitive science.
So, Leah, can I ask you to give us your take on why we've seen this huge surge with the arrival of ChatGPT and similar products in only the last couple of years? In layman's terms, can you tell us why all this has exploded onto the scene kind of all at once? What's going on here and what's the bigger picture?
I think it's three things. One is a much, much bigger compute power. So machines are much, much more powerful. We can store much, much more data. We can gather much, much more data. So the training data increased in orders of magnitude. So compute and data are the two. And then the third thing that really got it off the hook was putting the models that have existed in the background behind a nice user interface and making it really accessible to the whole world. So the technology behind ChatGPT was not groundbreaking. They had a few extra bells and whistles that they added on, but it was all developed incrementally and the community knew that it was coming. But I think making it available, making a nice user interface so that people can interact with it nicely, that was the third ingredient that led to the big hype that now is everywhere.
Now we've got all these different AI systems, whether it's ChatGPT from OpenAI or Google Gemini or Cloud from Anthropic, or a host of others. When I test the same piece of text across these different platforms, I get different results. Why does that happen?
So there are two reasons. Even if you give the same input again and again to ChatGPT or Gemini, you will get slightly different results, right? So it's not completely deterministic. It's not for the case that for the same input, you always get the exact same output. So there's randomness in these models by design. But also they're all trained on slightly different data sets. They all have slightly different architectures. They all have slightly different bells and whistles.
You're talking about models. What are models?
Well, we talk about machine learning models, I guess.
So machine learning, is that a kind of AI? Are they the same thing?
No. AI in particular is a term that's very hard to pin down specifically. But let's start with machine learning, which is one type of programming computers in a way that these programs solve a task and they themselves improve the quality with which they solve the task by seeing more and more data. And that's different from traditional computer programming or traditional algorithms where often a set of rules is hard-coded into the program. In machine learning, there's no such thing. We tell the algorithm what we want it to do in general, and then we might present it with examples of a task. So one example task could be sentiment analysis. So you give it a natural language sentence and you want the algorithm to tell me whether the sentence has a positive sentiment and positive attitude or a negative attitude. And you present it with lots of examples. And from these examples, the algorithm itself learns to recognize certain patterns that helps it to arrive at the correct output. And that's machine learning, these automatic extraction of patterns from lots and lots of examples rather than hard coding these patterns as rules into the algorithm.
And you have to give feedback to the machine learning to tell it, yes, you are correct, or no, you are not correct. So it learns the parameters, the boundaries of acceptable output. Do I have that right?
There are more than two types, but the two main types are supervised machine learning, where you give it the feedback exactly as we just described. But there's also unsupervised machine learning, where you just give the model a bunch of data and you let it figure out itself the patterns. And it might give you some groupings of the data points that are similar in one way or another. And then you, as a human, can go and interpret these groups of data points and try to make sense of it. So that's unsupervised machine learning.
So where does machine learning fit into what we understand today as generative AI? What's the connection here?
So there are many, many ways in which you can extract these patterns in a supervised or unsupervised way. And one way to do it are neural networks. So neural networks or deep learning, it's one approach to machine learning. And it has had an immense success. They are inspired by the brain. That's why they're called neural networks. They're large collections of nodes that are connected with weights. And through these large networks, you can pass inputs to get certain outputs. An input could be a sentence, usually represented as a vector, so that you can then run computations over this vector. And this is passed through the network. This vector is manipulated in order to get an output vector, and this output vector can then be mapped to an answer. So let's say our input is, again, a sentence, and the output vector would be a yes answer or a no answer. Now, each of the nodes is a little computation, usually a nonlinear transformation of the input. And the output of each node is reweighted by the connections to its following nodes. So the input is nonlinearly transformed again and again and again as it is being passed through the networks to the output. And what these neural networks do during training is they learn the weights between the different nodes. In today's neural networks, there are billions and billions of nodes with billions and billions of weights. And these are very carefully tuned in order to solve a certain task.
So the training data to build these, do they exist in the neural net, or are they simply the fuel that sort of allows them to form?
They're the fuel. These are the natural language text corpora that we currently have. And very specifically, one basic type of training that underlies all of the big language models that we have now, it's very simple. Your input is a prefix of a sentence, and the output is the next word. So if I give you as input, this morning I rode my bicycle to, then the model needs to produce the next word, which might be work, for instance, right? If the model produces the wrong word, then the weights inside the neural network are updated a little bit so that hopefully the next time the model sees the sentence, it will produce the correct word. But this is a very neat training task because you just need to collect all the text that you can possibly get your hands on, and you can just mask out individual words, right? So you don't need to manually label any training data through an expensive process. You don't need any experts whatsoever. You can simply put any text that you get into this network, and through that it learns the fundamental patterns and regularities underlying language. These models know nothing about grammar rules. They might implicitly pick it up, and there's a lot of work on trying to figure out to what extent they can reproduce these rules about grammar or semantics, syntax, but they're not explicitly coded in at all.
Is this the reason why neuro-machine translation outperforms the previous paradigms, like statistical or rule-based machine translation models?
I guess so. So you can only hard code so many rules, right? And there are always exceptions to these rules.
Yeah.
And in some sense, you can view these enormous neural networks as ingesting all these different exceptions by just looking at so many pairs of texts or so many examples of natural language.
So you've mentioned that the basic unit is essentially a sentence, right? So when it comes to how the systems handle and retain information, does that mean if we give a neural-machine translation system or any system based on the same principles a longer sentence, it becomes more challenging for it to produce an accurate output?
Yeah, that's a good point. So today's systems, they are not really bounded by sentences at all. And this goes back to one keyword that you also wanted to ask about, namely the context windows. So how long is the input that we can provide these models with? Or similarly, during training, when we do this next word prediction task, how long is the prefix that the models get? And sometimes they just need a very long prefix. If one sentence refers back to some building that has been discussed in the beginning of a document, it needs a lot of context, right? So the bigger these neural networks get and the more capacity they get, the better they are able to maintain this context and to keep it all in memory and make long-distance dependency assessments.
Okay, I think it's time to bring in our producer, Eric, here. As I mentioned in the last episode, Eric has agreed to be our AI guinea pig and will be sacrificing his real voice in the interest of demonstrating the magic of generative AI. Eric?
Yeah, thanks, John. So here I am. This is my real voice. And I just need some help from you guys to get me into my other voice for this episode. So if you could just... Yeah, if you don't mind. Yeah, that's almost... You got it.
Wow. Okay, that feels better. So, yeah, this is my new voice. Well, just for this episode anyway. I hope you like it. And by the way, we'll be discussing just how this is accomplished a little later in the episode. So I just wanted to demonstrate something that Leia was talking about in answer to one of your questions about how identical prompts can give varying or sometimes quite different outputs across different large language models. I've created a prompt, which I'll read out here, and then we'll just see what comes out of the latest versions of the big models from OpenAI, Google, and Anthropic. I'll be using the free versions, so listeners can feel free to follow along at home. And yeah, I know the models get improved very regularly, so I'll timestamp this at mid-October 2024. So the prompt is, tell me in under 40 words why I should believe anything you tell me. So here's what OpenAI's ChatGPT 4.0 came up with.
I'm based on a vast range of verified information and trained to present accurate, unbiased responses. While I aim to be reliable, always double-check important facts, as I may still lack context or have outdated knowledge.
And this was the output from Google's Gemini 1.5 Flash.
As an AI language model, I provide information based on the data I've been trained on. I can access and process vast amounts of information, but I'm not able to have personal experiences or beliefs. It's important to verify information from multiple sources.
And finally, here's what Anthropic's Claude Sonnet 3.5 had to say.
I'm direct and honest about my limitations, including the fact that I can make mistakes. I aim for accuracy and will tell you when I'm uncertain or need to qualify my responses.
And even when we put the same prompt into the same large language model for a second consecutive time, we can expect something different. Here's Claude Sonnet 3.5 once again.
I am direct and honest about my limitations, including potential errors. While I aim for accuracy using my training, I encourage verification of important information rather than blind trust in my responses.
So, John, what have we learned?
By listening to the three responses from different models, I do appreciate the last one because the last one is being transparent, and I do appreciate the honesty saying that, there's a lot of limitations. But then in terms of the explanation of the real question asked, why do we give the same prompts but then get different responses? I think the second one, the Google Gemini, gave a really good answer, saying that because we're not thinking here, we are generating things based on the data we have in the database. So it's okay, it's convincing. But I would vote for number 2, Gemini, and the number 3, but not for ChatGPT because I feel like you're not providing accurate information. It's factually wrong and it's hallucinating. But on the other hand, the system is claiming to say that I'm here to give you accurate information. Please trust me. And that's so misleading in every sense.
Because it's not accurate very often, as we know, and you certainly have to check everything. You have to be very, very wary of some of the stuff that gets presented to you through any one of these different models. The word token comes up a lot as well when talking about generative AI. What exactly are tokens?
Good question. So we probably have some idea about what a word is intuitively. In English, it's kind of strings of letters that are separated by white spaces. But defining this properly is very difficult. So in NLP language processing, we have agreed on some more formalized definitions of what a word is, and these are basically tokens. And these are the individual components that are being fed into the neural network model.
So this often means breaking up words, right? For example, the word what, with the apostrophe, could be split into 2 tokens, right? It's unlikely to be treated as just one.
Exactly. It goes even further than that. So ultimately, these models work with a vocabulary, so a list of all the tokens that exist in a language. Now, if we would enumerate them all for English, we would have an awfully long list, right? So instead, what is often done is break down words even further into components which repeat again and again. And that could be something like an S, a plural S. That's a useful word or token to have in your vocabulary because that you can reuse again and again. Or some prefixes like anti or un or pro. So the actual inputs to these models, we call it subword tokenized. So we break the words down into subwords, and these subwords are then put into the model. And the number of subwords is then much more manageable because these are the repeating kind of morphemes or little substrings of words that we see again and again.
Just to be clear, when you're writing a prompt in ChatGPT, it then tokenizes that text, correct?
I assume so. It tokenizes the text, and then actually each of these little tokens are mapped to a vector. So a string of numbers, because ultimately what all these computer models work with is numbers, right? We map words into a space of vectors where intuitively similar words end up in a similar point in the space. You can imagine them as 2 similar words, like cat and dog would be close together, but cat and office chair would be further away from one another.
The term parameters comes up a lot when we talk about large language models. Now, I'd assume that the bigger the number, like 7 billion or 500 billion parameters, that's talking about the size of the model. Those parameters are basically the connections in the model, right?
Yep. If you again think about the brain, we have lots of neurons in our brain which are connected with synapses too. simplify it very much. And you can visualize a neural network in a similar way, where you have lots of little compute nodes which are connected with weights. And every weight is a parameter. And this is learned during the training of this model.
So when we look at the term GPT, what does it stand for? What do each of those words mean?
GPT stands for Generative Pre-trained Transformer. Let's talk about the P first. That's the pre-training. And this is what we talked about before. So we have a randomly initialized neural network. And what you first do in order to get some meaningful parameter values, you pre-train it on the task of sentence completion or masked word recovery. So you input this sentence where the last word is missing. Today I rode my bicycle too. And then you train the model to predict the missing word work. And you do this again and again and again over enormous text data sets. And based on this, the model learns the ropes. So the basic characteristics of language, the basic dependencies between words in all sorts of languages. So the model is being pre-trained to do this, to basically generate language. And that brings us to the generative part, the G in GPT. So generative AI is AI that can learn from some dataset of text, for instance, and then generate new instances of the same type of data that are plausible, that come from the same distribution. And this could be text, this could also be images or voice or video. So the generative AI, it's not text-specific at all, right? We can also pre-train our models on images in a very similar way and make them generate images. Now the transformer, that goes a little bit more into detail. And this is the secret sauce of the most successful neural networks that have come about in the last 10 years or so. And this is what allows the models to make these long-distance inferences or to keep the long-distance dependencies. When you input a long sentence or a sequence of sentences into the model basically learns at each point, so for each word or token, which other words it really should pay attention to at that moment. And that might be a grammatical thing. So if you have a very long sentence where you refer with a pronoun to some entity that you have mentioned earlier on, the model should kind of know that this pronoun refers to this entity earlier on, right? Or it might be semantic, where you introduce a word at some point which is similar in its meaning or similar in the domain it refers to something you talked about earlier on. So the model, through an attention architecture, this model learns itself to pay the right attention to other tokens in its very long input. And to do that, as you can imagine, you need a lot of training data so that the model can reliably do that. And this is the transformer architecture.
So that paying attention to certain other tokens, that's different from the weights that are assigned?
It learns specific attention weights. Yeah. And actually it has multiple layers of attention, multi-layer attention or multi-head attention, this is learned. And each attention head has its own little role. So one might pay more attention to the syntactic dependencies. Others might be more focused on semantic dependencies. Some might do something completely different. So this is not necessarily interpretable. It's, again, the attention patterns that the model deems useful in order to solve the task that it's supposed to solve, namely completing sentences or generating human-like language in response to an input.
So exactly how automated is this process of creating attention in a network?
It's completely automated. So it's all the same game. You have your big neural network, you present it with an input. During training, you pass the input through the network, you observe the output. And if the output is not what you were hoping for, then you update the weights in some way. And there are algorithms to do this in the optimal way that maximizes the probability that the next time around, this input will lead to the correct output. And you do this again and again and again. So we talked a lot about the pre-training, the simple objective of learning the patterns in language, predicting the next word. This is all fine and good, and this is where it stopped until a couple of years ago. But after this pre-training phase, another phase happens now for the OpenAI models, and that's reinforcement learning from human feedback, which is another buzzword that you probably have heard about. And this is what gets the model to be really good to respond to instructions or to make seemingly natural conversations with its user. And that works by getting humans to judge responses to inputs. And they get 2 different responses. They tell which one they prefer. And based on these human preference data, which continuations seem more natural to a human user, the model is further trained and fine-tuned. And through that, it gets this notion of a continuing flow. And this might not be only with respect to the naturalness of the response. It might also be with respect to being politically correct, not producing hate speech, not producing sexist or racist or otherwise biased language. And all these constraints are imposed onto the model through this human feedback training mechanism. And that's super central for the kind of last little step that makes them really natural and also reasonably safe to use.
And do we have farms of people trapped in front of computers who are doing this job who are native speakers of English?
Yeah, I think we've seen that in the media. So OpenAI in particular, they employed lots and lots of people in Africa for very low salaries. But I think that they still have US American workers too, who are closer to the values that a US ChatGPT is supposed to.
We also spoke to Dr. Ting, a researcher working with AI and machine learning, specifically around detecting and interpreting non-linguistic aspects of speech.
Hi, I'm Ting. I'm from the School of Computing and Information Systems at the University of Melbourne. So currently, I'm a senior lecturer working on the mobile health domain via the acoustic sensing. This means we analyze the audio and speech sounds and try to identify the biomarkers from these sound signals to infer some of the health conditions to improve the healthcare delivery. Like the way you talk, like the pitch changes over time to infer your emotion, the pauses of your sentences to infer your depression states, for example. And we also analyze the coughing and breathing sound as well to infer some of your respiratory health conditions, for example.
You focus on the paralinguistic cues.
Yeah, that's right. Like not mainly on the linguistic cues, but on the paralinguistic cues, like how you talk instead of what you talk.
Yeah. So you're focusing on emotional state, physical state, those kinds of things that come through the voice. Not direct meaning, but for instance, if I've got creaky voice, what is that saying about my current health status, etc.? So how do you go about picking up emotion in these senses? What technology are you using?
So we actually analyze the emotion from the speech. For example, when I'm happy, I might have a higher pitch. So I can actually extract the pitch information from the speech and map it to the corresponding emotion. And for example, when I feel a bit depressed, maybe I will have more pauses when I talk. So I extract these silence regions and then use it to infer some of the the depression states, for example. But we are not only using solo features. We actually try to leverage the deep learnings to automatically extract more related information from the speech and to infer these emotion states.
So how are you defining deep learning in this context?
Deep learning actually is an algorithm that uses the neural networks to do some of the recognition or prediction tasks. So it's kind of like we refer it as deep learning because we can have many, many layers of the neural networks to make a deep network. That's why we call it deep learning.
Okay, guys, let's pause the conversation here for a moment and have a bit of fun while demonstrating another mode of generative AI. We've heard a lot about generating text, but what about other kinds of output? Listeners should now be familiar with AI-generated images and even videos, but as we're on a podcast, let's stick to speech and how speech that's generated doesn't sound like robots anymore. I mean, my voice in this podcast is an example of that. There's a real person behind this voice, me, Eric, and the intonation you're hearing is mine. It's just that the voice is not. And as it's the speech of one person essentially grafted onto the voice of another, we call it speech-to-speech. Different from typing in words and then generating a voice output. That's called text-to-speech. Now, I just want to play a short series of speech-to-speech cloned voices based on a single phrase and get a reaction from our guests.
Will you just stop it, please? I am sick and tired of it.
Will you just stop it, please? I am sick and tired of it.
Will you just stop it, please? I am sick and tired of it.
Will you just stop it, please? I'm sick and tired of it.
Will you just stop it, please? I'm sick and tired of it.
So, Ting, what's going on in that speech-to-speech example?
Right, okay. By the way, the quality is really good. I'm also surprised by the quality of the generated speech sound, actually. So for that one, generally when we want to convert one voice to the other's voice, we would look at both the linguistic information and the paralinguistic information. So for the linguistic information, we need to understand what you said, like the units of the text, like the words or the phrases. And on the other hand, we also need to understand the paralinguistic information, like your pitch, your emotion content, and how these different states alters this paralinguistic information. And by combining these two kinds of the informations, we can further synthesize the speech to different languages under the similar states if you want. So that's how the model actually processes with the two different streams together to generate the sound.
So, Leah, how do you explain what we've just heard, what's going on with generative AI and speech?
So in some sense, the text-to-text model that we have in ChatGPT, it takes the different tokens, maps it into some neural network representations, and from that it, again, produces the output as text. So there's very little that this matrix, this vector representation, has to do with the actual tokens that are the input and the output, right? So similarly, you can imagine taking as input sound waves, which is what our voice ultimately is, and mapping that into some high-dimensional representation and producing sound waves from that. Now, with the speech-to-speech, voice cloning, voice synthesis models, what happens is that the input voice is mapped to some specific acoustic feature representation of sound waves, which captures different properties of the sound. So that might be the pitch, the speed, the volume, the, vowel shape that you have in the sound. And based on this, the content and the properties of the voice can be analyzed. So you basically map the sound waves to the structured representation, and some of the structured representation will pertain to the pitch, it being a male or a female voice, the accent and so forth. And then there are machine learning models that can tease apart the properties of these sound waves that are the actual content from all the other information that gives you the voice and the tone and the accent and so forth. And once you can tease that apart, you can recombine the two components, and that gets you towards voice cloning.
And can I say I work in this field? I've worked in speech sciences for more than 30 years. The quality, the shift over time, and I've been around a long time, I mean, that is amazing quality, and the fact that you can replicate in all of these different accents, etc., is amazing. And I've been around when it's been very clunky, and you can hear, it sounds unnatural, it sounds artificial. That sounds perfectly natural. It's quite remarkable, the shift.
Yes, but as far as I understand, there are two places where neural networks and the really big transformer models really help. And one is when you try to map from the speech of one person to the speech of another person. So you basically want to generate text that sounds as if it's being said by the other person. To get this mapping really, really perfect, there's a big neural network in the middle, which is being trained, I assume, on speech, on texts that have been spoken by many, many different people. And then by all these people, many, many different texts, so that the model can really learn to tease apart the content from the form. And then the second important part is, once you want to generate the text, you need a model that can turn these structured representation back into waveforms. And that's another neural network, and these have been improved immensely over the last couple of years. So with speech and video, you have the temporality as well, right? Where there are very, very fine-grained time steps and the outputs change rapidly. So there is a little bit of an extra component to account for that. But apart from that, it's being able to capture the basic patterns. This is what these models are incredibly good at.
So, Ting, you can tell that emotional content comes through in these voice clone examples. But while we're all human and share common emotions like anger or happiness, there are also cultural differences in how those emotions are expressed. Could the model, for example, recognise that in Japanese or, say, Turkish, that frustration is expressed in a particular way and then incorporate those specific cultural elements into the output?
Yeah, that's a really good question, but I really don't believe the model can accommodate the cultural differences at this stage. So it will just use some general rules for the emotion characteristics of the voice and then apply it across different languages. It's really hard because we need to annotate the data first to understand the cultural differences and then embed these knowledges in the machine learning approaches, which is still an active research area, and I don't think it has been addressed yet.
It's not just about the language, it's about those paralinguistic cues that the AI systems are going to have to get on top of and understand that the variation is much greater than we presume, even when we're speaking the same language.
Right. I would say if we have some common patterns, for example, like the intonation decreasing and increasing common in two different languages, maybe if we have a huge amount of data to train a model to learn this kind of the correlation, it will work. But the difficulty lies in the individual differences as well, because it's not going to be common for one culture or one group. There will be a lot of the variations across the different individuals. So how to handle these subtle differences in the model will be another challenging problem as well.
How much data is enough to get a high-quality system?
We are talking about terabytes of data, so yeah, it's a lot. And it's the quantity. It is also quality to some extent. So there's a lot of work on data cleaning as well. It's not that OpenAI just scrapes the whole internet and puts it into its training algorithm. They strip away a lot of HTML markup and other noise that you do not want to have in the data. It's also very important to deduplicate the data because a lot of websites are there on the web many, many, many times.
Yeah, absolutely.
And if you're not careful, you get them overrepresented and you get a biased model. So this data cleaning is also super important.
And in terms of what you think the big limits are to current models?
Hallucination is one big limit, which I'm not sure we can get out of based on how these models are trained. We want them to be creative, right? We don't want them to just reproduce strings from their training data. We want them to produce genuinely new text. And then there's a very fine line between creativity and factuality. People are making the argument that we need a separate module in the system that can watch out for factuality. And there are some ideas about these models would look like. They are in the systems as we have them right now, but obviously they're not cutting it. And malicious actors can always tweak the models and get them to produce whatever language they want. So this is a big societal issue. And the scale is an issue now as well. There are predictions that reasonably soon, most of the language on the internet will be generated and no longer human produced. And I think the tipping point is not far away at all. So yeah, it's going to be tricky to distinguish human language from generated language.
I just want to ask about another limit in using machine learning models, particularly in the area of student assessment. Many universities use software like Turnitin to check student work for plagiarism. And now the software is making claims about detecting use of generative AI as well. The people marking the student essays, for example, will see a score or a percentage given by the software to indicate whether or how much generative AI was used. How reliable are those scores or percentages? Can we trust them?
Not particularly. So there are quite large fractions of false negatives. So where the model wrongly says this is not an AI, but it was one, and false positives, where the model says it was an AI, whereas it was not. I think these rates get even worse for non-native speakers. So they are more often falsely accused of AI usage, even though they might have used some other means of grammar checking their inputs. So I think it's still not recommended to trust these models blindly because they can introduce biases for different types of writers. But this is actually another big problem with the whole neural networks and deep learning. They are all black boxes in the end. We have no idea why ChatGPT gives a particular answer. We cannot trace it back through this huge neural network and take any conclusions about the reasoning in scare quotes underlying the model and how it ended up producing these particular words. So interpretability is a huge question. And we talked about future research directions a little bit, but interpretability is one. Efficiency is one, because we are burning insane amounts of energy by training the models, and it must become much, much more energy efficient, especially as more and more models emerge.
How would you compare those efficiencies in these models with the efficiencies of the human mind? Can you talk a little bit about that?
Right. So we all learned to speak at least one language during childhood, and the amount of input language we got from our parents and from the people around us was a tiny, 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 tiny fraction compared to the amount of language a ChatGPT-like model gets when it is trained. So there must be something in us that lets us learn language in a much, much more efficient way. And at the same time, while we are growing up, we are learning many, many, many other skills, social skills, motor skills, and so forth at the same time. So there is a way to do it much more efficiently. And one of the reasons is that we have, as humans, we get much, much richer signals from our environment. ChatGPT largely gets a signal about whether it predicted the correct missing word in a sentence or not during training, whereas we get audio signals, other sensory signals, social signals, and so forth. And also importantly, we develop goals. We have emotions, we have desires, we have feelings like hunger or tiredness and so forth, which kind of drive us to learn and to become better at certain things and to do certain things. So we have inherent motivations, and that's completely missing from AI at the moment, for the better or the worse. In some way, these current AIs allow us to understand a little bit better the roles that all these different properties that we have as human learners play in us learning so efficiently. So there's a big research direction which looks at AI models as kind of participants in psychological experiments and looks at how they perform different from humans and trying to better understand the human cognition and psychology.
Well, that wraps up this episode of The Secret Life of Language. Special thanks to our guests, Dr. Leah Frermann and Dr. Ting Dang, both from the School of Computing and Information Systems at the University of Melbourne. Producers for this episode were Eric Van Bemmel and Kelvin Parham of ProFactual, and Gavin Neighbour. The Secret Life of Language is recorded and mixed at the Howard Recording Studios by Gavin Neighbour and is a podcast from the University of Melbourne School of Languages and Linguistics. This episode was produced with some limited use of generative AI technologies. Be sure to keep up with every episode of The Secret Life of Language by following us on the Apple Podcast app, Spotify, or wherever you get your podcasts. The Secret Life of Language is licensed under Creative Commons Copyright 2024, the University of Melbourne. I'm Professor John Hajek, and thank you for joining us.